So when ATP breaks down into ADP, when it loses that phosphate, it technically releases energy. A lot of times you'll actually see a number associated with this. I believe it's, like I said, it's like negative 7.3 kilocalories per mole. You would never be tested on that number. Technically, the amount of energy released, as a matter of fact, would change depending on the conditions around it. Because remember, delta G is dependent upon temperature. Remember the formula. So technically, it's not that exact amount, but sometimes you'll see them say that amount. ATP is renewable. So what will happen is an exergonic reaction will happen, and like I said, the energy from that will build ATP. It'll hook the phosphate on. So reactions release energy, that hooks the phosphate on and makes ATP. Then you have a reaction that needs energy, so we break ATP back down and release the energy. So ATP literally is an energy carrier that temporarily, in that little bond to the third phosphate, stores the energy. Now, how long does it store energy? Not very long. About 10 million ATP are consumed and regenerated every second. So this is not something that holds on to energy for a long time. That's why if you hear like somebody can only go, somebody falls into a lake, they can only go about 6 minutes, I think is like the maximum, give or take, without brain damage. Why? Because you run out of ATP. You don't get any oxygen when you're underwater, and the ATP can't store energy for minutes and hours and whatever. ATP stores energy only for seconds. So once you run out of oxygen, your ATP starts to get depleted very quickly. And without ATP, all the endergonic processes in your cells can't happen, which means your cells start to die. And it's only a few minutes before that happens. So ATP is something that carries energy very quickly, just grabs it and passes it. It doesn't store energy for a long term. And this picture you should understand. The idea that ATP is capturing, it's built by capturing the energy from exergonic reactions, and then when the phosphate breaks off, it releases the energy. So it just temporarily kind of holds on to that energy and then passes it along. All right, these are just some pictures. In this case, it changes the shape of the protein in a transport protein like what we talked about in the sodium-potassium pump. In some cases, it allows a protein to move, like your muscles contracting. ATP is responsible for allowing your muscles to contract. When long, skinny muscle cells basically become short, fat ones. That's basically what's happening when you flex a bicep. All those bicep, hundreds of muscle fibers contract. ATP is responsible for that. That's why when like your pet dies, sadly, if you've ever experienced that, you'll find that it's cold and it's stiff. It freezes. That's rigor mortis. The muscles can't move because when ATP runs out, everything just locks. The muscles can't slide anymore. So anyway, so that's just examples of how passing the phosphate along can move things along. All right, and that brings us to the last thing we're going to talk about today, which is what's called activation energy. Just because a reaction is exergonic doesn't mean that reaction will happen fast. For example, I have a bottle of peroxide here. The reaction of peroxide breaking down into water is exergonic. It breaks down into water and oxygen. You know this because you've seen when you put it on a cut, I talked about this, that we have an enzyme called catalase and it bubbles. And so this is an exergonic reaction, it releases energy. If that's the case, I shouldn't be able to go buy peroxide because all the peroxide on the planet should have already broken down because it's an exergonic reaction. So obviously something prevents every exergonic reaction from happening right now this second, or we would all spontaneously combust. There'd be no life on the planet. So there has to be something controlling it beyond the fact that some reactions require energy. Even reactions that release energy need sort of a kickstart to get them going. And that kickstart is called activation energy. And this is what prevents my peroxide, for example, from breaking down. The activation energy to break it down is high enough that peroxide breaks down very slowly. Now, if I keep this bottle for 5 years or something, probably what I'll feel is the bottle will start to bloat because some of the peroxide is breaking down into oxygen. And if I put it in a beaker, light is a catalyst that actually speeds up the reaction, and so it would happen even faster. But if I was to put a drop of blood in this container, within 3 minutes, all the peroxide would be broken down. So enzymes, what we're going to find is that enzymes are a way of lowering this activation energy, this kickstart to get a reaction started. All right, so without activation energy, basically every reaction would happen, and everything would die. The whole Earth, everything, remember, everything's going towards a state of equilibrium or a state of entropy. Some reactions, if you heat them, that provides the activation energy to kickstart it. If molecules are moving faster, they're going to hit each other harder, which makes them more likely to react. Think about two cars. They're traveling very slow and they bump each other. They may not scratch each other at all. Two cars going very fast and they hit each other, they're going to do a lot of damage. So sometimes heat is enough to get a reaction going. So I have a little bottle to show you this demonstration, which nobody there can see. So, all right, so this, I'm going to show you a better graph in a minute, but this is sort of an idea of what happens. Here's my reactants, and this is the energy, the amount of energy in my reactants. Here is the amount of energy in my products. The difference here is delta G. This is what we talked about yesterday. This is an exergonic reaction. It gives off energy. But notice this hump here. This is me throwing that ball up in the air. The reactants have to sort of get primed and ready, bump each other in the right way in order to react. That is activation energy. That's what keeps my peroxide from just breaking down right here in the bottle. Even though the overall reaction, the net change, is exergonic. But it needs that kickstart, and without that, it can't get going. Notice this little investment, it's going to get it back right here. So the net change is still just here to here. So, bottom line, heat can sometimes overcome this barrier. But enzymes are very specific, and you have all kinds of hundreds of enzymes in your body that lower activation energy for a specific reaction. So if I just want this reaction to go, I can use an enzyme, my cell can use an enzyme that will speed up just that reaction and no other reaction. They don't change delta G. The net energy change stays the same. But what does change is the activation energy necessary to get the reaction going. So a reaction that might have occurred over a long period, for example, digesting your food, probably take you a couple weeks to digest one meal without enzymes. With enzymes, within a few hours, your food is completely digested. So that is just one example. And I showed you, and I told you with the peroxide, if you put peroxide on a cut, it breaks down immediately. Within seconds, that peroxide has broken down. The peroxide your cells make as a waste product can't hang around for years. It's toxic. So your cells have an enzyme, it makes the reaction happen much faster. Would the reaction happen anyway? Yes, but it would take much longer. So enzymes speed up reactions by lowering the activation energy. This is just an example. You have an enzyme sucrase. Sucrose is table sugar. It is an exergonic reaction to break sucrose into glucose and fructose, disaccharides and monosaccharides. But if I go to the store, I can go buy sugar. It's not all broken down, and I can probably leave it in my cabinet for 10 years and it won't break down. But if I add this enzyme, it'll break down almost instantly. Why? Because to get it to that transition state, that activation energy is too high under normal conditions for it to break down, and the enzyme will speed it up. So tomorrow we'll talk about how they do that. This is the last graph I want to show you. So this is delta G. This graph will be on a test. Guarantee you. You will see this graph. There'll be multiple choice questions about what is this pointing to, what is that pointing to. Delta G, the net energy change, is always just going to be the difference between the reactants and the products. So that's this. Notice that enzymes don't affect it. What enzymes do is they lower that activation energy to kickstart it. So this tall one is our activation energy normally for this reaction. And this short one here is our activation energy when an enzyme is added. The enzyme lowers that hump that has to get the reaction started so the reaction can happen a lot faster. So tomorrow we'll talk more about how it works, but you should know those three things from a picture graph like this, which is actually number 7 on that worksheet, by the way. It's a graph like this. If you were given a graph without an enzyme, and they ask you draw in a dotted line showing what the enzyme would do, you would just make a dotted line anywhere under the first hump. Enzymes lower this. There's not a right place to put that dotted line. It just has to go somewhere lowering this hump from this higher level to some lower level. That's how enzymes work. They lower the activation energy to get a reaction started.